So we're going to finish up what we're looking at in Chapter 8 with Section 8.2, Systems of Linear Equations still, and we're going to talk a little bit about matrices. So we're going to talk about how do you write the augmented matrix of a system of equations. And they have to be linear in this case, so system of linear equations. We're going to write the system of equations from the augmented matrix. Then we're going to learn how to perform row operations on a matrix, including learning some shorthand for that operation. And then we're going to solve a system of linear equations using matrices. So this is the plural, matrix is the singular. Okay, so here's just a little intro to matrices. If you've ever worked with Excel, an Excel spreadsheet is basically a matrix where it has columns and rows, and you can put things in this arrangement of columns and rows, and then it's called a matrix. So each number has two subscripts, an I and a J. The first subscript tells you what row you're in. So see how in row 2, the first subscript for each A is a 2. The second subscript tells you what column you're in. So you can see that when you're in row 1, column 2, your subscript is 1, 2. So it's not a 12, it's a 1 and then a 2. So this matrix has m rows and n columns. The numbers in there are usually referred to as the entries in the matrix. So A subscript 2, 3 is talking about the entry in the second row and the third column. So this makes a way that's much more efficient for computers. We write the augmented matrix just has coefficients with spaces in between them, and then a vertical line, and then the constant. So we have the 4 and the -2, the coefficients, the vertical line, and the constants. So this is called the augmented matrix. So in the background are the variables, the pluses, and the equals, but we don't write them, they're understood. So this is way more efficient when you're using a computer to solve linear equations. So just the coefficient matrix would be the 3, 4, 4, -2, without the constants, the 7 and the 5. So the augmented matrix represents the system of equations. So if you're missing any variables, you need zeros to be placeholders. So this system of equations could be written with the matrix 5, -1, -1, and then a 0. Then we'd have a 1 for the x, a 1 for the y, and a 0 for the z, and then a 5 for the constant, 2 for the x, 0 for the y, -3 for the z, and then a 2. So this is the augmented matrix that represents this system of equations. Okay, so then we're going to go back the other way and make sure you can write the system of equations if you can see the matrix. So I usually remind myself, especially with bigger problems, that the first column is the x's, the second column is the y. So I'll have x plus 3y equals -3, and 2x minus 5y equals -4. So you can see that it's a lot more writing. And usually we put the little brace to indicate this is a system of equations. So writing out the system of equations with all the pluses and the equals is just a lot more writing. So it's much more efficient, especially as the systems get larger, to use a matrix representation. So there's three kinds of row operations you can do on a matrix. And if you keep reminding yourself, these are really systems of equations. So this is a system of equations. And remind yourself that if we do things like interchange any rows, all we're doing is switching the order of the equations, and it should make perfect sense to you of why you can do that and nothing changes. So switching the order of the equations in a system does nothing to change the solution. So replacing a row by a non-zero multiple of that row, that's the same thing as multiplying both sides of the equation by some number. As long as it's not zero, we know that's a legal thing to do. So the only thing that's a little trick here is you can replace a row by, you can take 3 times row 1 plus negative 2 times row 2, and you can put that in either row 1 or row 2. We'll use capital letters for the row we're going to, the new one. So if you take 3 times the old row 1, remembering to multiply both sides, and then negative 2 times the old row 2, then you can multiply through, get 3x plus 3y plus 3z equals 15, and negative 2x plus 2y minus 10z equals negative 4, and you can add those together and get x plus 5y minus 7z equals 11, and that can replace either the first row or the second row. Okay, so there's a shorthand for this row operation. I just kind of demonstrated it of what if you want 3 times row 1, the old row 1, so lowercase, and always add a negative 2 multiplied by rather than subtracting 2. If you're always adding, I can pretty much guarantee that you'll make a lot fewer mistakes than if you're sometimes adding and sometimes subtracting. So rather than subtracting, multiply by the negative number and then add. So first we write the system of equations corresponding to the matrix. So we can see this is x minus 3y equals negative 3. And then 2x minus 5y equals negative 4. Then the instructions ask us to take negative 2 times the old row 1 plus old row 2 and make that new row 2. So we take negative 2 times row 1, get negative 2x plus 6y equals 6. Add 2x minus 5y equals negative 4. And hopefully you're seeing why you would do this. And you'll get y equals 2. So now your matrix looks like 1, negative 3, negative 3, 0 x's, 1 y, and 2 in the row 2. But if you're remembering that you can read this back as an equation, you can see that y equals 2 by just working in the matrix. Okay, so let's do number 22 in class together and see why you would want to do those steps. So what we want to do with all of this is to solve a system of linear equations using matrices. So the goal is to get it in what's called row echelon form. So you want the entry in row 1, column 1 to be a 1. So this is not in row echelon form because row 1, column 1 is not a 1. This one might be and this one might be. Then the first non-zero entry in each row after the first row is a 1. So here I see the first non-zero entry is a 1. And it's to the right of the first non-zero entry in any row above. So here the 1 is to the right of any rows above, and here I have no 1s. Here the 1 is to the right. And then the last condition is any rows that contain all zeros appear at the bottom. Okay, so there's going to be a matrix method for solving a system of equations. And this is in words, but I'd rather show you an example because I think it will make more sense. So in this case, the reduced row echelon form is given, and they want us to write the system of equations corresponding to this given matrix. Well, we can see that this first one is pretty much done. We have that x equals -4 and y equals 0. So the solution is -4, 0. And this is a consistent system of independent equations, which we know because we got a solution. Okay, so number 30 says that x plus 4z equals 4, y plus 3z equals 2, and the bottom row doesn't give us any more information. So in fact, if you get a row of all zeros, you already know that you are consistent dependent. Okay, so what we're going to do here is solve. Well, actually, we know we're dependent. So we're going to let z equals t. This is how we find that infinite family. So x equals 4 minus 4t, and y equals 2 minus 3t. So the solution family looks like 4 minus 4t, 2 minus 3t, t. So it's the set of all x, y, z such that they look like 4 minus 4t, 2 minus 3t, t, for t is any real number. So this is consistent system, but dependent equations. Okay, and let's do number 27 in class together. So this last one says solve the system and just figure out what's going on. So again, we'll do this one together in class. And that's all we're doing in section 8.2.